Hi, I'm Martin Looker from Silicon Labs, back with another Simplicity Studio 6 video. Today we'll be looking at the software components available in Simplicity Studio that can accelerate your product development. There are a broad range of these. They cover things such as protocols like MQTT if you're working with Wi-Fi parts, plus components for or useful to use with other wireless protocols. They also cover hardware peripherals, including communications like UART and SPI, plus higher level abstractions supporting buttons, LEDs and sensors. All these components offer software APIs, removing the need for you to develop your own, and in some cases including them will add supporting configurations too. Adding a BLE service software component will also configure your GATT database, while adding a peripheral component will configure your pins appropriately. And you still retain flexibility over these when using them via the configuration settings available in the software component. You'll find links to many helpful resources in the video description, so please follow them for further guidance. I'll be sticking with the EFR32xG24 Dev Kit board used in previous videos, as the wide range of onboard sensors and peripherals make it a great prototyping platform. I'll be building on the Bluetooth Health Thermometer example application that I used in previous videos, and making a change to the Bluetooth Health Thermometer service part of the GATT database. This is included via a software component in order to take advantage of the ready-made APIs. Including this using the software component means the GATT settings can't be altered in the lower level GATT configurator. They need to be altered via the software component configuration, and I'll show you how. We'll also take a look at how those APIs are used by the application code. I'll also be adding a new RGB LED software component, which will set up an appropriate pin configuration for the board, and then use the included APIs to set the color of the LED according to the measured temperature. So let's dive into Simplicity Studio and take a look. To manage the software components, we need to open the project configuration or .slcp file. Going to the projects page, I can double-click the project in the projects tree. The Software Components tab then allows components to be explored. This list currently shows all components, both those installed to the project and those that are not. You can filter the displayed components using the controls along the top, and also search for components, useful if looking for a particular component. For now, let's take a quick look at some of the components already installed into the example project. I'll do this by filtering to installed components only. Let's start with application components. Here we see the assert component, used to abort the program if an assertion is false. The log component, used to log events to the UART in the application, plus a basic timing component. We'll return to the Bluetooth components in a moment. For now, I'll skip ahead to platform components. These are concerned with the hardware on both the board and chip. Here, we can see a component for a simple button that is used by the app to lock in a specific temperature when pressed, and which in turn relies on GPIO components. We'll look at a similar component for RGB LEDs in the second half of this video. Under board drivers, we can find the driver for the onboard temperature and humidity sensor, used to measure temperature, and in turn that makes use of the I2C component for communications. Under services, you'll find components supporting non-volatile memory storage, the power manager, and timers. And finally, under third-party components, you'll find a tiny implementation of printf that is used in log messages. Returning to the Bluetooth section, we can find that most of the Bluetooth features are also brought in via components. These include support for general protocol handling, core Bluetooth features, and management of the GATT database. We also have support here for features like the OTA updates and various services which also appear in the GATT database, like the Device Information Service and the Health Thermometer service around which our application is based. These are just the components that are installed in the current application, and you can extend it by installing additional components. Say if we were to make this into a battery-powered device, we might install the Bluetooth battery level service. Now, all these components can be very overwhelming, but when you find what you need, they will greatly speed up your application development. The best way to approach this is to choose an example project as close to your final project to use as your starting point. If you're creating a Bluetooth device, choose the empty Bluetooth project rather than an empty C project. Similarly, if you're creating a Bluetooth health thermometer, choose that example instead of the empty Bluetooth project. By doing this, the core components your application needs will already be in place as soon as you create that example application. Similarly, once you have your starting project, look for components to help you at the highest level possible by using the search box. If you need to add a temperature sensor, search for one. Only drop to a lower level, say I2C, and write your own driver if you don't find the sensor you need. For each component, you'll find a brief description, a list of dependency components that, if not already installed, will be installed when the component you are looking at is installed, plus a link to the documentation for a component, if you want to explore the APIs before installing. We'll now look at this health thermometer component in a bit more detail. You may recall from the previous video that we were unable to make any edits to the health thermometer service in the GATT configurator tool. This is due to it being brought into the project via this software component. If I click the Configure button, that will take us to a set of controls where we can edit the values we would otherwise expect to edit in the Bluetooth GATT configurator. Let's change the temperature type from the more generic body value that was seen in the previous video to something more specific like finger. Next, we'll move over to Visual Studio Code and look at how the APIs this component adds are used by the application. The first thing I'm going to do is click the Workspace Refresh button to ensure that the change I made in Simplicity Studio is applied to the VS Code project. Let's look for the files brought into the application by having the component present in the example project. Under the Simplicity SDK folder, we can dig into the App, Bluetooth, Common, Health Thermometer folder and find the SL Health Thermometer.c file, which contains the implementation. If I select its matching header, I can right-click and select Go to Definition to open up the header file. Note that these files are linked into the project from the main SDK instance. Changing them should be avoided if possible, as those changes will also be applied to any existing or future projects that make use of them. If you really need to change them, consider copying SDK files into the project, so changes only affect the project they are copied into. I'll open up app.c to see how these APIs are used by the main application code. First, the SL Health Thermometer.h header file is included to provide access to the APIs. The SL BT Connection Close CB callback function is implemented in the app. This is called whenever a connection is dropped, and the periodic timer used to take and transmit readings is stopped here. Next, the SL BT HT Temperature Measurement Indication Changed CB callback function is also implemented. This is called whenever the temperature measurement characteristic receives an alteration to its indication settings. When this is turned on by a remote application, the periodic timer is started with an immediate call to the timer's callback function to generate an immediate reading and indication. When indications are turned off, the timer is stopped. These two functions serve to notify the application when indication settings are changed or a connection is closed, so that the application can react appropriately. As these are callback functions into the application, the developer must implement their contents. Finally, in the timer callback function, following a temperature read, the Health Thermometer API SLBT-HD temperature measurement indicate function is called to provide the new temperature reading and indicate the update to a connected device. This final function is implemented in the APIs, removing the need for the developer to work with lower-level APIs to buffer the value and transmit the indication. Before I recompile, I want to show the process of adding a new software component to the application. For this, I will look for the simple RGB PWM LED software component and click the Install button to begin installing it. You are then prompted to select an instance name. For this component, you could have multiple RGB LEDs in the application, and this serves as a handle to the instance. For recommended names, like this RGB LED 01, Simplicity Studio is aware of the components on the board and will automatically configure the correct pins to drive the red, green and blue channels of the LED. Clicking the button will install the component and create the first instance. If you want to have multiple RGB LEDs, the Add New Instance button can be used to add more. As there is only one physically on this board, you would need to create a custom name and configure it with appropriate pin and timer settings. We'll take a quick look at how this configuration works by clicking the Configure button. The top row contains configuration for all instances, including the PWM frequency and resolution, along with polarities for the red, green and blue channels. Then we have settings for each instance, including the timer settings and pins for the red, green and blue channels. If I open the user guide for the board, we can see the pins selected here match those in the documentation. We can look at this at a lower level too, by opening the Pin tool. In here, we can see the same pins have been configured to work with the timer. So by adding the recommended instance to the board, the pin setup has been done automatically in an appropriate way for the board in use. This has saved time compared to configuring timers and pins at a lower level. For custom instances, you can still save time by configuring the pins for that instance in a similar way, and so avoid having to work with the Pin tool. Next, we'll look at the APIs the software component has made available to the application by returning to Visual Studio Code. As I've made changes to the project in Simplicity Studio, I'll refresh the workspace. Once again, the implementation C file can be found in the Simplicity SDK folder, and we can view the header file that goes along with it. I've already updated the app.c file to control the RGB LED. The first thing to do is add any headers to app.c to access the component. This is not done automatically by adding the component, as application code is always left untouched. Looking at the APIs, it looks like the initialization function for the RGB LED needs to be called first. However, this is taken care of already during system startup in auto-generated code, which you should not edit, by the way, as recompilation may remove any changes. So all that is left to do is set the color as required in the application code using the SL simple RGB PWM LED set color function. For this video, I'm going to keep it simple by using a static set of colors. The SLBT on event function is used by the BLE stack to indicate events to the application layer. In the boot event, after beginning advertising, the LED is set to dim white. When a connection is opened by another device, that is changed to bright white. And when the connection is closed, it is returned to dim white again when advertising is restarted. The other place where the colour is changed is in the app periodic timer CB function, which takes temperature readings and issues indications. If an indication fails, the colour is returned to bright white to indicate the device is connected. Where an indication is successful, the colour is set according to the measured temperature. Blue for dangerously cold, cyan for slightly cold, green for normal, yellow for slightly high, red for fever hot, and finally magenta for dangerously hot. I'm now ready to compile and flash the application, and the bootloader is already in place from the previous video. Let's see how the final application with updated and new software components works. I have my board on the left with a translucent bottle cap to avoid saturating my camera. At the moment, Bluetooth is disconnected, so the LED is showing dim white. On the right, I'm running the Simplicity Connect mobile app. To begin, I'm currently on the scan page, and to test the bright white LED colour, I'm going to connect to the device from here. Upon connection, the LED switches to bright white. It will remain this colour because indications have not yet been configured. Next, I'll disconnect, check the LED returns to dim white, and move over to the Demo tab. The Health Thermometer interface provides a more readable way to view the temperature. When I connect, the LED will likely very quickly turn blue, due to the device being at room temperature, which would be dangerously cold for a human body. I'll swap the display to centigrade, as that matches the temperatures at which we'll see the LED colour changes. Also, we can see the device is now reporting it is measuring temperature from a finger. This is the change I made in the Bluetooth Health Thermometer API's software component. Now, I'll heat the device and we'll see the LED move through the colours as it warms. This might be quite quick as I'm using a heat gun. As it warms, it will work through blue, cyan, green, yellow, red, and finally magenta. When I turn off the heat gun, we'll see the temperature drop more slowly due to it cooling naturally. Magenta is displayed when the temperature is over 40 degrees, red when it drops below 40, then yellow below 38, green when below 37.3, cyan below 36.5, and finally blue when below 35. Now we've reached the end of the video, we've updated a software component that was already part of the project, altering one of the values in the Health Thermometer GAP service, and taken a look at the APIs the component provided to ease development. We've also added a new software component to control an RGB LED using PWM. In addition to using the APIs, adding the component also configured timers and pins appropriately for the dev kit. In both these cases, the use of a software component has saved development time, both in configuration files and providing ready-made APIs for use in the application layer. When exploring software components, especially when looking for an appropriate one to use, remember to make use of the search box in the Software Components tab to aid discovery. Also, check out the links to relevant resources, which you'll find in the video description. Thanks for watching.